So good morning. Hello, everyone. I'm Matt Fetro with the Air Force Research Lab, the Department of the Air Force. Really pleased to be here this morning to try this out and give you a virtual guided tour of our work here at AFRL in New Mexico. I've been with AFRL a long time, usually as an optical physicist, but the last few years I've been able to lead our outreach programs, which includes our STEM education programs, it includes our tech transfer, and our business partnership programs. And so I know many of you in the room. I'd like to meet you all. What I'll try to do is go through what we're actually doing on the base and give you a sense of our Kirtland Air Force Base work here in New Mexico using a combination of Google Earth and a few slides and some videos and whatnot. I usually do this on Zoom. Hey, it's a sort of a COVID invention, but since we can't be on the base today for a bunch of reasons, including the fact that you're really busy folks, hopefully in the next 40 minutes or so, I'll give you a little sense of what we do. This works a lot better if you ask questions as you go. This is one nice thing about being in person. It's kind of hard for me to watch the chat. Please, if you're online, use the chat, try to somehow get my attention. And if you're in the room, just raise your hand as I'm talking, right? Or even do one of those things that I do on Zoom, right? The overly expansive, gestures to try to get someone's attention. Because I really do want to answer your questions and make sure you get a little bit more of a sense about what we're up to. Does that make sense? All right, it seems kind of crazy, but let's give this a try. Get rid of that right now. So many of you know, the Air Force Research Lab is really the technology arm of the US Air Force and now the Space Force as well, right? Space Force is not just a Netflix show, it's actually the 6th branch of our military, and we're pleased to provide technology for the Space Force as well. AFRL is a large organization, but we're distributed across the country for lots of reasons, both historical and sort of geographic needs. Our main location is in Dayton, Ohio, and we're actually broke up into technology directorates, so basically technology business units. And so many of our business units are in Ohio as well. Things like aerospace systems, manufacturing, sensors, and medical. We've got places up in New York, Rome, New York, that do information technologies. We still work on weapons, munitions, down at Eglin Air Force Base. And here in New Mexico, it's our 2nd largest location, where we work exclusively on space technology and something called directed energy, which is mostly lasers and microwave weapons. We're mostly at Kirtland Air Force Base and some locations off the base, and we've got about 2,000 people here in New Mexico. About half of those folks are federal employees like myself. The other half are contractors, right? Industry team members that come to work every day at Kirtland Air Force Base to help us with our mission. We're a small lab, national lab for New Mexico. About $500 million a year worth of money flows through our place. We're a couple thousand people. Just by contrast, Sandia might be 10 or 12,000 here in New Mexico, a much larger lab on Kirtland. One of the things I've learned over the pandemic is I can't actually drive the computer and talk at the same time. You'd think I would learn that over the course of the last 18 months, but I'm still not much better. So I give this presentation a lot to folks that aren't from New Mexico. In fact, one of my favorite things to do is give it to like college students from New York State who probably aren't going to travel here and give them some sense of what we're up to. So bear with me as I zoom in, right, to our great state. A lot of times folks really don't have a sense of where New Mexico even is. But of course, you all know that New Mexico does a lot of technology development, a lot of space development. You heard from Casey Durad in New Space New Mexico just previously. We're based at Kirtland Air Force Base, which is right in the heart of Albuquerque, essentially, and we share the runway, of course, with the Albuquerque International Sunport. Kirtland Air Force Base is a really interesting base. It's very large physically. That crude outline that I drew, that black line is really where the base outline is. That's physically larger than Washington, D.C., just a ton of square footage, a ton of different things going on there. It's also an unusual base in that we don't have a primary mission, flying B-52s like they do out of Louisiana. We have a lot of different missions. There's something like 100+ tenants, if you will, organizations like AFRL that are on that base. Other big ones for the Air Force are like the Air Force Operational Test and Evaluation Center, the Nuclear Weapons Center, and of course other non-Air Force tech like Sandia National Lab and others as well. Before we jump onto the base, I want to mention that most of the AFRL work is done near the airport on the west side of the base. Not all of it. We've got a lot of research locations throughout the base, but most of our main offices and where we'll talk about it is right here. Before we actually go on to the base, I wanted to mention a couple of things. We're moving more and more of our operation, it's a small amount, but it's an increasing amount off of Kirtland Air Force Base. And so, for example, we have a relatively new research lab that we share with University of New Mexico. And this little picture here is part of it. In this particular case, we're doing research in how to make satellites better using automation, using 3D printing, using machine learning, those sorts of things. So we deliberately chose to put that facility off the base. There's nothing sensitive about that work. We want to partner with industry and university people, folks from other countries as well on that work. And so that's a growing part of our effort, is to get out in the community and do the research where it makes the most sense. Another example of our off-base location is in collaboration centers. And so we've just opened up a new center on Central and Nob Hill called Q Station. It's really an aerospace collaboration center, an incubator space, really trying to connect Air Force people, other government folks with industry and academics, right, to try and create value both for the Air Force, the Space Force, but also for the state of New Mexico and the city. So that opened up, I think, probably back in October, and it's been really, really powerful for us so far in ways to really connect with the community. All right, enough of that. If we were doing this in person, we would probably muster someplace at a parking lot, all get on a bus and head through the Truman Gate, which is here. This is another great way for me to do it because I get really car sick on buses. But those of you that have been through the base, I flash them some credentials. And the first stop I want to go to is on the directed energy side. So this particular building is called the Davis Advanced Laser Facility. And you notice, hopefully you can see this cursor. This is the actual laser building here. And here, this is a big hangar. And so, it's interesting to me to look at this overhead and see how close that laser facility is to the runway. And that's no accident. And so I want to talk just a little bit about what we're trying to do with lasers in the Air Force, and then take you into one of the laboratories we're working on those high power lasers. I need a driver or more skills. So we've had a long history in the Air Force of working in laser technology, back probably 40, 50 years. These days, our goal is to put lasers on airplanes. And these are airplanes that do something else. So many of you may know that many years ago now, we did the Airborne Laser Program, which was tremendously successful. But it was a chemical laser stuffed into a stretch 747. As I understand, it wasn't the standard 747, it was the extra long version, because that's the one it took to actually get all those people, all that equipment in there and make that system work. Very successful, but that's all that plane could do. And while that was great, what we'd really like to have is, as you see in these photographs, planes that have a mission, defend the country, defend the US, something like that, that also has lasers on it, mostly to shoot down missiles. Currently, for an engagement in the Air Force, we could anticipate seeing missiles coming at our aircraft and our pilots. We're very good at shooting those down with other missiles, but it becomes this sort of medieval game of who has the most missiles. And so ideally, and in the future, we'd like to basically shoot all those missiles down with lasers, because these are electric lasers now, not chemical lasers. And as long as you've got electricity and turbines on the aircraft making electricity, you can continue to shoot down missiles. So we've got sort of a roadmap here showing an increasingly capable set of lasers on increasingly sophisticated aircraft. On the right-hand side, what we'd like to see eventually is having lasers actually built into the aircraft. That's not happening today, but just like with your car, if you go buy a new car, you're going to get, radio's going to be built in, air conditioning is going to be built in. Those used to be add-ons, right, back in the day. We also want to build future aircraft that actually have lasers built in. So it's kind of funny, I briefed this chart a lot. It was probably the 100th time I briefed this when someone stopped me and said, give me a break, what's a 10,000 watt laser or a 100,000 watt laser? How big is that? I don't have a real sense for that. And so I put together one additional chart that gives you just a sense of what we mean. A common laser pointer, and I actually brought some show and tells because we're in person for a change, is about 2, 3, 4, 5 milliwatts, right? 2, 3 or thousandths of a watt. And it's pretty bright. This is a green one. Hopefully it's a green one. And that's not bad. I see that as being quite bright. But it also has a warning label on it, right? So folks recognize that it can be damaging, at least to eyes. In order to get something a little more interesting and more dangerous, you have to go up a factor of 1,000 or so, and that's that middle graphic. That's this laser here. And this laser is a 2-watt laser, right? Two whole watts. It doesn't sound like a lot, but I actually took the batteries out of this. They don't last long anyway. They're rechargeable because it would be very, very unsafe to fire this laser in this room, right? This can really damage eyes, and not all of us have, eye goggles on. This is actually power enough to burn through paper in just a couple seconds. We do a lot of demos popping balloons because it's a killer for balloons. And so that's 2 watts. They are commercially available. I don't think they're legal, like certified, like they've got but you can get them on Amazon. So even a 2-watt laser, that isn't even remotely enough power to be useful or be called a high power laser from the lab's perspective. You go up another factor of 1,000. So now we're 1,000,000 times brighter than the laser pointer. Right now we're starting to get into a laser that's interesting for the Air Force. So what I think I'm going to do next is try to take you into that laboratory. It's the laboratory right here. I'm going to jump to a movie to do that. At least I hope I'm going to jump to a movie. So this is one of our fiber laser labs. We probably have half a dozen like this doing different types of research at Kirtland. Traditional optics lab, for those of you who've seen something like that before. These 2 gentlemen are part of our contractor team, and you can notice they've got goggles on, right? This laser is extremely dangerous. Funny thing, if you're wearing the laser goggles, you can't see the laser beam or what you're doing. So he's using a guy on the right in the plaid is using a video camera to actually see the laser. The laser is right in the center, and I'll zoom in on that. It's called a fiber laser. And it's one of the couple of kinds of solid state lasers we're currently working on. As the name suggests, the optical properties are based around fiber optics and telecommunications. And the fiber optic is that thing that's wound around the mandrel there in the center. It might be glowing blue or purple or something. As the light goes around the fiber, it continues to be amplified, right, to where it comes out the end as a high power laser. That fiber is maybe hundreds of meters long, and it could be stretched out and it would work just well, but our lab's not 100 meters long, and nor is an aircraft, and so packaging is very important as well. So in making a laser weapon, which is essentially what we're trying to do to shoot down missiles, the laser itself and creating a high power laser is hard enough, right? It's not easy at all. There aren't very many of these kinds of devices around, but that's really the beginning of the challenges. One of the other things that's a big deal is that these lasers, even though they're electrically driven, aren't particularly efficient. Just like your air conditioner is not very efficient, these are maybe 10, 20, 30% efficient, which means if we're making thousands of watts of power of light, we're also making many thousands of watts of heat. And so we do a lot of research in cooling technologies as well. This is just a laboratory setup. So these are actually cooling lines, right? Water being used to keep things cool. If you leave this laser on long enough without cooling, it'll burn itself up. This is the backside. Melda Atencio, my friend here, looking at some of the cooling equipment. I mentioned that we have about 1,000 federal employees on base. About a quarter of them at AFRL, about a quarter of them are military, mostly officers with technical degrees from AFID and other places like the Air Force Academy. And they often get an early assignment in their career at AFRL before going off and doing other amazing things. So I want to talk just a little bit about what happens when lasers hit things. And I usually rail on movies a lot at this point. You've all seen lasers in movies, probably. You probably each have your favorite. We should do a poll. I usually do that on Zoom, right? What's your favorite laser movie? Mine's Real Genius because I'm that old, and 1985 was a great year for laser movies. But oftentimes, Hollywood will portray a couple things out of lasers. First of all, they always make a sound, right? A pew sound or some sort of cool sound. Well, that's not true, right? There's no inherent sound from the laser. Sometimes you can hear background noise from fans and heating equipment, but there's no sound. The other thing is you can always see the beam, which is cool. Maybe even go out slow or fast, right? But unless something's reflecting the beam back into your eyes, there's no reason to see that. Right? You can see where it ends, just like I gave for this example, but you can't see it traveling unless I block it somehow and reflect that light into your eyes. And then the third thing, and the most annoying thing as a guy at AFRL, is that usually whatever gets hit by the laser just explodes in a ball of fire. Well, that doesn't happen either, right? Unless there's something combustible that you're hitting, like a gas tank, then there's no reason for it to do that either. So I've got a couple of videos that show you what the laser actually does to metal. One's metal and one's another object. And it's a little bit like welding. This is a very short clip. But as I turn this on, well, right now you can see those traces are actually camera traces, right, from sparks flying off this metal plate. The laser's coming from the left to the right and hitting this plate. And as I play it forward, little pieces of the metal are being blown off just from the intense heat of that small spot of light heating up that metal. So again, nothing too dramatic happened. Nobody was blown out of the room. And this effect reminds me a lot of welding, if you've ever seen welding occur. In that case, electricity is being used to deposit a really, really intense spot of heat, and sparks sometimes come off. It's the same thing with this laser, and we're just using light to make that heat at the target. So this last thing I'll show is a little bit longer clip, and I made a mistake and I forgot to bring my challenge coin. If you were to come on base, one of the things we love to do is we take these commemorative coins. They're sort of large and colorful, painted on both sides, really cool. And we'll knock a hole in it for you using this laser. And so this is a real-time video of that occurring. And so as I play it through, the laser's coming through this lens and being focused right down onto the challenge coin that's right here in the middle. And this is real time, and this gets to be one of the third problems or challenges we have with lasers. As this maybe a couple kilowatt laser, a couple thousand watts is being put on this thick coin, first it starts to burn through the paint, and that's what you see the smoke from. Also why they say to clean off your welding part before you start welding, because it could actually catch on fire. It's now burnt through the paint. It's starting to burn through the multiple layers of metal. These things are relatively thick, still burning through. You can either hum or just think about the Jeopardy theme song in your mind as we're doing this. Still burning. We're going to need a bigger boat. You can see now that it's actually started to light a fire on the paint on the backside, which is kind of cool. There's flame back there. And it'll finish up here in just a second by burning through the backside paint completely. And we'll have a laser burn, we call it, a burn coin. So you can imagine that if you were shooting down a missile in an aircraft, you might want to do it a little quicker than this, right? Because the plane is moving, the other plane's moving, missiles are moving, everything's moving. And so not only do we need to do this more rapidly, there's a really challenge in holding the laser beam on the same spot on the missile during all of that time. So there's a lot of pointing and tracking, we call it, acquisition, tracking and pointing, and a lot of computers involved, a lot of control loops to keep that laser beam right on the same spot. Because while more powerful lasers will do this much more quickly, it still takes a few seconds. Just think on the order of a few seconds, not instantaneously, right? For a hole to burn through the object, maybe that missile, and go ahead and defeat that threat. So that's what I've got on lasers. Any questions? I'm moving along. We've got a couple other topics, because this isn't all we do at AFRL. I know you have questions. Sir? Yeah, so the question was related to for an airborne application, which is pretty much all we work on. Where does the electricity come from? And absolutely, yeah, we go ahead and just pull that right off the engines, the turbine. They actually have a lot of power. And the other thing too is we wouldn't use this laser for very long, and so the total drain on the power system is fairly modest. But I will add that stuffing all of this stuff in, not the lab version, but the real version, into an airplane is super hard. Those modern aircraft, they have no room in them, right? They've already taken up all the room for other stuff. Right? And so finding the place to put this, getting the power to it, getting the heat out of these devices is a real challenge. All right, we're going to jump back, I hope, to Google Earth, because I wanted to say one other thing about directed energy before moving on to space. I think I want to say one other thing. So I mentioned Kirtland's very large, and hopefully this doesn't make you car sick like it does me watching the video. But even though most of our work is done near the airport, most of our labs are near the airport, we do avail ourselves of Kirtland, and it's really unique terrain and frankly sparse population, the Air Force Base, to do other sorts of things. This is one of our microwave facilities. It's called HRDF, and I can't recall what HRDF stands for. It's a really cool building that was designed specifically for microwave experimentation and testing. And you can tell it's kind of in the middle of nowhere. In fact, what you can't tell, it's kind of in a canyon. And so we do a lot of propagation experiments with microwave weapons here. Microwaves are essentially intense radio waves in short pulses, and we're developing those technologies exclusively now to defeat electronics. Electronics could be, computers, laptops, those sorts of things, or they could be the electrical systems like in small UAVs, which is becoming an increasing annoyance for lots and lots of people. Anyway, so this is one of our facilities. It's just a great place to actually try out things. The mountains, right, provide shielding so that, we don't let any of that, microwave radiation get into places it shouldn't be. So I think I'll stop on directed energy because we have a few space topics to cover as well. And I also want to make sure we get any questions answered. So I think this is going to jump again. Close your eyes. Again, much quicker than the bus ride. That's about 30 minutes we just did. So jumping over to, again, near the airport, fact, this is very close to the FAA tower. I want to talk about 3 things that the Space Vehicles Directorate does, and then show you one of them, one of our integration labs for small sats. So this building is called the Battlespace Environment Lab, and it really is the center for one of those 3 things. I think about rockets and satellites a lot when I think about space, but what this team does is actually think about space, right? What is in space? We often think of space as being a vacuum, nothing being up there, and that would be great if it were true. There's not much in space, but what is in there is really nasty. Mostly from the sun, you get protons, electrons, all sorts of interactions with the magnetosphere and the upper atmosphere of the Earth, and all of that radiation, all that stuff creates hazards for our satellites. These are the people that study that and try to figure out how to mitigate those hazards. So as an example, as satellites are flying around and around, they pick up electrons that were actually spit out by the sun. Those electrons will attach themselves to the satellite. And if you've ever done the shoes on carpet thing or the balloon on the hair, the same thing can happen to satellites. Satellites can actually shock themselves by collecting a lot of electrons and having one part of the satellite shock another part of the satellite. So these folks understand how that happens and understand ways to mitigate that. And that's what we call the battle space environment, because it has to sound a lot more Air Force-y than what I just said. The other group, the other headquarters that's near there is this group, and this is the second main thing we do for satellite technology development. And these folks make parts. It's the components division, and they make all the pieces and all the subsystems that go into satellites. Satellites are funny because they're not a whole lot different than your cell phone. They're just bigger, more expensive, and they fly a lot higher. So there's batteries in there, there's solar cells that charge those batteries, there's radios, electronics, all sorts of thermal issues, structures to keep the whole satellite together, and that's what this group does. They work on parts for better performing and cheaper big satellites, and they're also working on miniaturized parts, right, for this new wave of small satellites that sort of the new space age has brought forward. So that's their main headquarters as well. I have a bunch of cool movies that show their work, and we're not going to get to them. Because the third thing I want to talk about is, for me, the most fun, and it's the third thing we do is we build satellites. We build small satellites typically for experimental purposes. And this is one of our 2 integration facilities, assembly facilities for those satellites. I want to talk a little bit about the kind of satellites we work on and then take you into that facility, just to give you a sense of how that work is done right here at Kirtland. We're not the only group that does this. There's actually similar facilities at industry partners across Albuquerque and across the nation. This is just our own particular brand. So just to provide a little context, artificial satellites that orbit the Earth come in a huge number of sizes and a number of purposes. They're mostly, at least for the Air Force, about communications and about taking pictures of stuff on the ground. It's not all we do, but 90% of what's done in space is really about communications or pictures. So on the left, you've got a very large satellite. It's a Boeing 702, one of their products. It's about 5,000 kilograms. It's kind of hard to see, but these little things here are people in clean room suits with the little hats on. So this thing is, I don't know, 30 feet tall, 15 feet in diameter. It's a big satellite. It takes its own rocket to get to geosynchronous orbit, which is way up high over the Earth. That's a particular spot you may know that is still orbiting the Earth, but it happens to be so far out and going so slowly relatively around the Earth that it matches the rotation of one day of the Earth. So it appears to be stationary over a particular spot over the Earth. One of the weather satellites that NASA runs happens to be parked almost exactly over Santa Rosa. And it just it goes around the Earth, and Santa Rosa goes around as well, right, with the sun, and every single day, which I find fascinating. The advantage of going that high is it can see at geosynchronous orbit, you can see half of the Earth at the time. You can also talk to half of the Earth at a time, right? So it's really, really advantageous. But it's so far away that A, it's expensive to get there, so you better build a big satellite, and B, you need a lot of power. So the satellite, like on the left there, 702, is about 300 million, 250. It might go on Black Friday sale, I don't know, but they're super expensive. And then on the right is a version that we're making, and I'll show you it being built in our laboratory. That's a small satellite called Shark. It's about 30 kilograms. And it's twice as big as the smallest satellite that we've ever made, which is this guy. This is a copy, we just didn't finish it, of a satellite we launched a few years ago. We just stopped making it. We didn't stuff it with electronics or solar cells, and then we also obviously didn't launch it. And I want to talk about these a little bit because these smaller satellites have more and more capability, They're not nearly as capable as a Boeing 702, but it's a growing capability as things get miniaturized, and it's certainly enough for us to test out things. So we often fly satellites of this size or of kind of this size at AFRL, because that's all we need to do to actually test our particular experiments. The other thing is this doesn't go up on its own rocket. It could. You could buy a huge rocket and send this up. You'd just be wasting a lot of money on a huge rocket. And so the other thing that the industry's come up with is ways to launch these more effectively, and I want to show you that as well. This would be about $50,000 worth of parts, but we actually spend a lot of money on these because all of the money goes into labor. Every time we make one as an AFRL, we do it differently, right? We're testing new things, and so there's a tremendous amount of labor in design work. There's a tremendous amount of labor in assembling all these custom satellites, and then the testing as well, I'll show you. It's probably no surprise that we don't fix these if they don't work in space. There's only been a few things that have ever been fixed in space, Hubble being one of them. And so it's a bad day if you make one of these, you spend all the time to do it, and then it doesn't work. So we test the daylights out of them on the ground to make sure that they're not, if they're going to break on the ground, not in space. I've lost track of what I'm supposed to be doing. Talk amongst yourselves. No, I'm just joking. I remember now. And then I went into the wrong laboratory. There we go. So this is, as I mentioned, one of our two small satellite integration labs. They look similar. This is very typical clean room environment, if you will, for manufacturing something that you don't want to get dust or particles into. These are actually some of our students from a couple summers ago. We have a large number of college and high school students that participate in our internship programs every year. Yay, I'm the outreach guy, right? And it's great because they get to learn about how to do satellites and how to apply their education to a real problem. We actually learn a ton from them as well because they bring a ton of energy and new ideas to our organization. The Shark satellite, which we're seeing them build here, was an experiment in communications. All it was doing was relaying messages between the ground and this satellite and a satellite called Globalstar to do some real cool text messaging experimentation. And so these folks are going through the process of stuffing it full of electronics. Again, it's all handwork these days so far in the kind we build. They're made of aluminum. They're kind of lightweighted, although they aren't particularly lightweight. Mass is not as important as it used to be. These are patch antennas, these gray things. When it's launched, we're not quite sure which way it's going to be pointing. You've got a direct TV antenna, you've got to kind of point it right at the satellite. Well, we're not sure that's going to happen. And so these antennas radiate in all directions, because again, it's a bad day if your satellite goes up and you can't talk to it, because it's now useless. That doesn't happen very often. And then now it's outfitted with a whole set of solar panels. There's two different kinds on here, some small cells and some larger ones. Power is a big deal. These satellites are in low Earth orbit, so half the time they're in the daylight and half the time they're at night. It's about 45 minutes each. And so they have to charge up during the daytime side and then have enough battery power to survive and be active, on the quote nighttime side. And so we put as many solar panels as we can. Early on in these small satellites, there was a lot of deployable panels, right? They would pop out to give you even more stuff. But again, if that spring doesn't work, or the latch doesn't come loose, you've got a bad day because you've just flown a brick. Many of you in the audience may understand why this is shaped this way. So this is a shorter version of that one. All of these satellites of this configuration are called CubeSats. And it's funny because this is not a cube, even I can figure that out. But sort of the minimal size of a CubeSat is 1/3 of this. It's 10 centimeters by 10 centimeters by 10 centimeters. And that form factor doesn't have to be that way. The satellite doesn't care in space what shape it is. It allows us to do some really cool launch choices. So as long as you're a number of cubes, this happens to be 3 cubes, the one in the picture is 6 cubes, then you've got some choices on how to make your launch a lot better and not buy your own rocket. There's actually a lot more choices these days, but this is the one I'll tell you about. So this particular testing, before we get there, testing. We do all sorts of tests with this. We shake them, we bake them, we put them in vacuum, we operate them when we're doing those things. Sometimes we don't operate them when we're doing those things. In space, it's brutal, hot, cold, radiation I mentioned. Getting there is even worse, right? If the satellite has to survive to get to the launch pad, the ride to space is awful. on a lot of rockets. And so we just test them and test them and test them, which is probably why I've got so many test shots in here. Before we get to that, though, I want to show you this is how we end up launching these. So if you're going to follow the CubeSat form factor, you can actually put these not on their own rocket, but as cargo essentially into space. So what these folks are doing is they're launching that 6U CubeSat inside of a Peapod, it's called. It's essentially a big Pez dispenser, if you're of an age to know that candy, right? And so they push the satellite into this aluminum box. There's a spring at the bottom of the box, and they snap the lid on. When this thing gets into orbit, you unhinge the lid, and the spring pressure just pushes the satellite up into space. So as long as you can get this thing into space on some other rocket, then you've got a way to actually launch that. It also sort of compartmentalizes the problem so that this satellite, if it were to break or something on the way up, it's stuck in its box and it doesn't hurt other things that might be going up with it. So it's a really neat idea that we did not come up with. Here they're actually putting the satellite on a shake table. It's essentially a giant speaker, a really big speaker that's programmed to mimic the vibrations of rockets, which is kind of cool too. In addition to building satellites, there's a ton of industry in testing, making test equipment, understanding reliability, all these other sorts of fields that go with the space domain. More testing, still more testing. It's a bad day as well if you get to this stage and you find out it's not right, because oftentimes it's a design flaw. You end up tearing lots of things apart, redesigning it, and starting over again, which again, not cost effective. So that earlier frame had our 6U CubeSat Shark being stuffed into one of these Peapods. There's 4 of them here. And there's a company called Nanorex, which is a startup company that's actually a broker. They work with NASA to be the intermediary between folks that want to get things launched and folks that have launch capacity. NASA has launch capacity, NASA has a space station. And so we worked with Nanorex. There are 3 other satellites now going up with ours in this CubeSat configuration. All of those get packaged yet again now into a big box. I think the space community is really, really fond of boxes because everything's got to be in a box that's then boxed. And this is sent to the Cape. So what ends up happening, and this one happened, this actually goes up, that Pelican case goes up with those 4 satellites in there as cargo to the International Space Station. So when they're setting up either the Northrop Grumman version or SpaceX's Dragon capsule, it's going up with all sorts of supplies to the space station, right? 3D printers, lettuce. They sent up chili recently, or chili seeds, I recall. This goes up with it. The astronauts pull that cargo in, then they, by hand, end up putting it on the end of the maneuverable arm. And so, and this is a shot of that arm. Now you can see, I don't know, quite a few of these Nanorex packages there, these Pez dispensers. They point the arm, light fuse and get away. They point it in a safe direction and go ahead and open the lids. And then since the space station is in orbit, obviously our satellite is now moving fast enough to stay in orbit as well as it drifts away. So this last frame I'll show you is a couple of the satellites at a distance, sort of drifting away from the space station. So the cost of launching these particular satellites using the method I described is just much, much smaller than obviously launching your own rocket and things like that. And so that's another thing the industry's really done, is come up with novel ways for ride sharing, partnering and whatnot to buy down the cost and provide more frequent launch opportunities. That has in turn just fueled this idea of different things we can do in space because they're now technically available and also cost effective. All right, I think that's what I had on space. And in fact, I should have had some sort of big finale thing to do on base. Maybe we could get back in the bus and do donuts or something, but I don't think I actually have anything. So with that, I would like to see if there's time for a few questions. Yes, ma'am, way in the back. If I understand the question is about risk. Are you talking about risks to the people that work at AFRL or risks on the satellite launch business? Which risk? Yeah. So 2 that come to mind, and the one that my laboratory is very aware of is the speed of technology change. right? And making sure that we're either keeping up or better yet ahead of that. And that's a real risk for us. Decades ago, the Defense Department, particularly for space, was the primary funder, and the pace of development was something that we sort of drove, frankly. That's not the case anymore, and so we have to be a lot more agile and a lot more aggressive, frankly, in order to keep up with that pace of change. The other thing that is related to space, I think is interesting, is we are more concerned than we used to be about the risk of space debris. You may have heard that there's a lot of objects in space. Those objects sometimes bump into each other. And I find that an interesting topic because we're currently hoping to deorbit objects. That's our plan. I mean, that's better than leaving them in space, but that just really disperses them into the upper atmosphere. And so I think another interesting thing we have to think about is how will we sustain space? Because space is huge. I mean, there's a very, very small chance that things will hit each other. It's imaginably vast. But I think we learned in other domains, maybe in the land and in the oceans, you can't just keep putting stuff up into one particular place and expect that to be sustainable. So that's another thing we're working. Other questions? And one other back here, sir. Yeah, so that's a great question. The question I'll summarize is essentially when you're on the ground in Albuquerque or in a lot of New Mexico, you can see things in space, right? So how many things are up there? How big do they have to be? And of course, the answer is it depends. It's always the answer. But just to give you some context, mostly what you're seeing are objects that are close to the Earth, if you can see them by your eye. And they're usually be able to see them in the morning and in the evening when those objects are illuminated by the sun, but it's still dark down here. You could go out and look at them today, right now, but I can't see through all that blue atmosphere that's so pleasant. So there are thousands of objects in low Earth orbit, many thousands, either leftovers from the 1960s or SpaceX's latest Starlink constellation. So there are a lot of objects up there. These are too small to see with the naked eye. In fact, they're very difficult to even see with telescopes and with radar. A lot of the cool objects that you see sometimes, you go, wow, you're out at night camping or something, or things like, used to be the space shuttle, now the space station. Those sorts of objects, very, very large satellites are easy to see. Starlink satellites, the SpaceX constellation, are again maybe this big. They're not nearly as big as that Boeing 702 that I showed you. And I think they're pretty difficult to see unless there's a lot of them with your naked eye. But telescopes can see them. And the astronomer community has been a little grumpy about the fact that these streaks of light are going to come through their astronomy images, more and more frequently as people put more stuff in space. Other questions? I know, so you had one more. Yeah. So we mentioned innovation and doing things more rapidly. And the Air Force, I've been really pleased, has really stepped up to this challenge. So in addition to a bunch of other programs, we have a new group called AFWERX, WERX, right? That's really looking at working with businesses and industry in different ways, much more rapidly. And because now we have a Space Force, we also now have a SpaceWorks, right? Which is aligned with AFWERX. Same thing, they're just announcing today a whole new series of funding opportunities to try to get at orbital debris mitigation much more rapidly. So our team actually includes a bunch of these SpaceWorks and AFWERX people. Our facility at Q Station is sort of an AFWERX and SpaceWorks node, if you will, right, a location. And my deputy on the outreach team is actually Gabe Mounts, who's also the deputy for SpaceWorks. So we're really thrilled to be part of that because we think that for a portion of our business has to move that way, has to move that fast in order to really be effective for the nation. Yes, ma'am. My laboratory only works on physical sciences and engineering, those sorts of things. And so a lot of our staff have math degrees, engineering degrees, my own degrees in physics and whatnot. When we do our STEM outreach programs, right, to try to help inspire young kids to get excited about jobs of the future, I usually go to computers, frankly, because there's so many sorts of things that are, whether it's satellites there's a computer inside this thing, right? We talk to it with computers. We collect the data and database it through computers and all sorts of things. And so and computer science, computer technology is a fairly low entry point. You don't need a ton of fancy equipment to learn and things like that. And so we've been trying as our laboratory to encourage young people to consider careers in computer science. Computer engineering, there's lots of different flavors, which I'm not that knowledgeable on, but anything in that area I think is just going to be huge. Randy? We have burnt challenge coins, and if I was a man, I'd have brought one here today, but I completely forgot. Not as much as it needs to be. So it still exists. As part of our outreach programs, the question was about Maker Hub Express. We're a big fan of maker spaces, both for our staff members and for teaching young people about how to do hands-on work. So we created a mobile version, finished it up just about the time the pandemic happened. And we're not stuffing 14 kids into a trailer to do stuff. So we need to reinvigorate that and get some programming for that. The vehicle exists, all the equipment exists, but of course it doesn't help anything unless you get that equipment out with knowledgeable people into the community doing good work. And so we still need to do that. Sir. So for low Earth orbit satellites, it's going to be the speed of light. It's radio wave speed of light. So you're talking, tens of milliseconds. To get out to geosynchronous orbit where you can see half the Earth, that's a problem. I forget, it's maybe a third of a second round trip. It's a relatively long number, at least in computer terms. And then historically, all these things have been custom made. The protocols, the frequencies we communicate, all of that is custom for satellites. That's starting to change as constellations get bigger and whatnot. So unlike my cell phone, right, which is either running Android or iOS, everything about satellites has historically been custom built. And we're looking for standards, we're looking for companies to offer software and whatnot that everyone can use, because that has to get better, right, as we proliferate the number of satellites. Awesome. I thank you all again for your attention and joining us on this experiment.